Let's start with continuous and discrete time signal. In continuous time signal, the independent variable is time is continuous time t, and in discrete time signals the independent variable is discrete time n. How to represent continuous time signal? It is x of t. And how to represent discrete time signals? That is x of n, where n belongs to an integer. Discrete discrete time signals are obtained from continuous time signals by a process called as uniform sampling. What is the name of the process? It is uniform sampling. And what is this? It is discretization of time axis. It is important. So let's see how a signal, how a continuous time signal is discretized by uniform sampling. We have a signal xt equals to e to the power minus t. Now if we have a switch which is closed at t equals to nts means every integer ts. So the discrete signal will be x of nts. Graphically, the continuous time signal will be e to the power minus t versus t. It is look like this, and x of nts will be this. Now, if t equals to 0, then nts will be how much? 0. If t equals to 1, nts will be ts, because we are putting the value in n. Sorry, if t equals to 0, then it is sorry, x of nts we want to know. So if t equals to 0, it is x of 0, and if t equals to 1, it is x of ts. If t equals to 2, it is sorry, t equals to ts, then it is nts, of course. If t equals to 2ts, then it is x of 2ts. If t equals to 3ts, then x of 3ts. So in the time axis, nts axis, it is 0 ts, 2ts, 3ts, and so on. The dotted line represents the continuous time signal, which is x of t equals to e to the power minus t, and in 0 it is this x0. It is in ts, it is x of ts. 2ts, it is x of 2ts. For 3ts, it is x of 3ts. If we look at the continuous signal, then zero ts, 2ts, 3ts, and so on. It is x of 0, it is x of ts, x of 2ts, x of 3ts. So this is the continuous signal, and this is the discrete time signal, which is represented by x of nts. Now if we see the basic signals, they can be represented by continuous time signal or discrete time signal. Let's move to our first example, which is unit impulse signal. It is important. Continuous time unit impulse signal is represented by del t equals to 1 into del t, where this 1 is represented the area of impulse signal, which is 1 or unity. Graphically, if we represent it, del t versus t, it will be look like this. It is 1, which represents the area of impulse signal. So if we define the continuous time impulse unit impulse signal, then first is del t equals to 0 for t not equals to 0. Del t is non-zero for t equals to 0, means t equals to 0, del t is infinite. You can say that I have write here 1, but here infinity, because this 1 represents the area and the value of del t is infinite at t equals to 0. And last one is, if we define the area, which is represented as integration minus infinity to infinity del t dt equals to 1. In another way, 0 minus 0 minus, oh sorry, 0 minus here and 0 plus, if you say this, then you can also say the area is 1. 0 minus to 0 plus del t dt. Okay, so you can write the definition of del t by these three ways. Next is discrete time unit impulse signal is represented by del n equals to 1 into del n. This 1 represents the value of impulse signal at n equals to 0. Graphically, if we represent it, then it will be look like this. This value is 1. Make note that I have saved this value for del n, and for del t I have said it is the area. So if we write the definition of del n equals to 0 for n not equals to 0, del n equals to 1 for n equals to 0, and summation from minus infinity to infinity. What is the value? It is n equals to minus infinity to infinity. Del k equals to 1. So we can say the definition by these 3 ways. Here the summation represents the area in case of del n, and in case of del t, the integration from minus infinity to infinity represents the area. Now let's look some properties of continuous time impulse signals. First one is sampling. Del at equals to 1 by mod a del t. Second is, if we have del minus at plus b, then let's common minus a into t minus b by a, and it is 1 by mod a del t minus b by a. Third one is, if we have ft del t, sorry, we know del t is only defined for t equals to 0. So put the value 0 in the function ft, put the value of t equals to 0 in ft and multiply with del t. Number 4 is similar to the third one, ft del t minus t naught. We know this del t minus t naught is defined t equals to t naught. So put t equals to t naught in ft and multiply with del t minus t naught. Number 5, minus infinity to infinity ft del t dt. We know ft del t is minus infinity to infinity f0 del t from the third property. Because f0 is constant, so f0 into minus infinity to infinity del t dt. We know the area of del t is 1, and this whole thing represents the area, so it is f0 into 1 equals to f0. So this can be right minus infinity to infinity ft del t dt equals to f0. Next, can you guess what the next property will be? It is ft del t minus t naught. We know this will be f t naught into del t minus t naught, integration minus infinity to infinity dt. This value is again 1 because it represents the area, so it is f t naught. Okay, so it will be our next. In our next lecture we will see some more signals like step signal, ramp signal, parabolic signal. So stay tuned.